next speaker is Wenhao Ou from Chinese Academy of Sciences, and his report title is The Rational Curve in Compact Kaehler Manifolds. Thank you. Let's welcome Professor Ou.
Thank you. Thank you for the introduction. And I would also like to thank the organizers for inviting me. It's my great honor to present my recent work here. So my title is Rational Curves in Compact Kaehler Manifolds. So I will work on compact Kaehler manifolds, which is a notion in complex geometry. And complex geometry is very related to algebraic geometry. So we will first start with some background. So first, I study geometry, so I would like to introduce the notion that and the targets I'm studying. So they are manifolds. The notion of manifolds at the beginning, it is about real manifolds. So a real manifold, it is a topological space which are locally the same as an open set in Rn, and this n will be the dimension, the real dimension of this manifold. Of course, Rn is a manifold. And maybe the first non-trivial example will be sphere. So the two-dimensional sphere, which we can visualize in this our three-dimensional world. So locally on a sphere, we can take a local piece, and this local piece, we can do some deformation, and this local piece will become like a square in R2. So this sphere has the dimension 2 as a real manifold. However, we notice that if we do this deformation, then we will lose the shape of the sphere, because we know that the sphere, there is some curvature on it. It is not flat, but this open set in R2 is flat. To deal with this problem, so we want to have some intrinsic notion of manifold that we can keep track on the shape of the manifold with our, say, for example, embedding in some larger spaces. So to do this, Riemann, he introduced the notion of Riemannian geometry in 1854. So briefly, on a manifold M, we can endow a Riemannian matrix G. So a Riemannian matrix we view as a distant functions on N. And together, Mg is now called a Riemannian manifold, and G is the Riemannian matrix. So for example, here we visualize that the upper edge of this local piece is shorter than the lower edge of this piece. That distance is measured by certain Riemannian matrix. So this is the of Riemannian manifold. It's on real manifolds. And I study complex geometry, so my object will be complex manifold. It is a straightforward extension of the notion of real manifold. A complex manifold, it is a topological space which are locally the same as an open subset in Cn. So we just replace Rn by Cn. We also know that C as a topological space, it is the same as the real plane R2. So a complex manifold of complex dimension n is automatically a real manifold of real dimension 2n. So let's look at some simple examples. For example, Cn, it is a complex manifold. N is any positive integer. We also notice that Cn, it is not compact. If we want to work with compact object, we can compactify. For example, we can compactify C1. In this case, the one-point compactification works very well. There is a complex structure on this compactification, and there is only one. This is P1. This is sometimes called a rational curve or Riemann sphere, and so on. So this is the first example of complex manifold. It's one-dimensional. So in higher dimension, we can do something similar. But the correct compactification is the following one. So for Cn, I will attach n minus 1 dimensional projective space. So for example, for n equal to 2, I just attach C2 a P1. So if we do this together, we'll get this n-dimensional projective space Pn. So this is the so-called the projective space. This is also a complex manifold. There are more examples by just taking holomorphic functions and consider their zero locus. For example, we can consider finite many holomorphic functions in Cn and consider their common zeros. They will found some so-called complex subvariety of Cn. And the regular locus or the smooth locus of them will be complex manifolds. And also we can take their their closure inside Pn. We will get some submanifolds in Pn. Now, a Kaehler manifold is the extension of the notion of Riemannian manifold. So a Kaehler manifold is a complex manifold X endowed with a Riemannian matrix G. And we require this Riemannian matrix has very good compatibility with the complex structure of X. I would note that there are complex manifolds such that there is no Kaehler structure on it. So Kaehler manifold from special families in the family of complex manifolds. There is another more precise definition of a Kaehler manifold. So a Kaehler manifold is a complex manifold endowed with a Kaehler form omega, which is a one differential form, and it is closed and positive. Now let's look at some examples of Kaehler manifolds. So the projective space we have just seen, they are compact Kaehler manifolds. Indeed, on this projective space, there is so-called a Fubini-Studi form of Fubini-Studi matrix on it, which is the standard Kaehler form or Kaehler matrix on this projective space. Every submanifold of a Kaehler manifold is a Kaehler manifold. So indeed, this is very easy to see because we only need to restrict the Kaehler form of the Kaehler manifold to the submanifold. This will give a Kaehler form on the submanifold. In particular, every submanifold in Pn is a Kaehler manifold. Every closed submanifold in Pn is a Kaehler manifold. So for these submanifolds, they are also called projective manifolds because they are inside some projective space. So there is a criterion to see whether a complex manifold is a projective manifold. So this is due to Kaehler in 1954. He proved that a Kaehler manifold is projective if it has a positive line bundle. For projective manifold, there is also a very important theorem due to Chou. So Chou's theorem says that every closed submanifold in Pn can be defined as the common zero of finite many polynomials. In other words, every submanifold, closed submanifold, is an algebraic submanifold. So algebraic is just related to these polynomials. Polynomials are given to algebraic. So for projective manifolds, we can use algebraic methods to study them. That's why there are a lot of more advanced results which are proved for projective manifolds. There is also a very special properties for projective manifolds. So projective manifolds contain plenty of submanifolds. So for example, we can visualize these points by the following argument. So projective manifold can be embedded in this Pn. But we know that Pn is the disjoint union of Cn and a copy of Pn minus 1. So we can cut this Pn minus 1 we can cut our submanifold by this Pn minus 1. This will give us a smaller submanifold of the first submanifolds. So by proceeding like this, we can produce plenty of submanifolds of a projective manifold. So this is a very special property for projective manifolds because there are compact Kaehler manifolds which only contains a point or itself as submanifold. So it is a curious problem to see how far general Kaehler manifolds are away from projective manifolds. So there is a very important result due to Wazan in 2004. She proved that there are compact Kaehler manifold X, so the dimension is at least 4, which are not homeomorphic to any projective manifold. So the topological type of compact Kaehler manifolds are much more than those of projective manifolds. So the goal of our study is to classify compact Kaehler manifolds. So let us start with the simple case, the case of one-dimensional manifolds. So every compact complex curve, so one-dimensional manifolds are also called curve. Every compact complex curve is projective. And we can roughly classify them according to their genera, GC. So genera is the plural form for genus. So we can roughly classify them into 3 classes. So the first one, the genus is 0, then this C is isomorphic to the P1, the projective line that we have just seen. In this case, C is also called a rational curve. So this is the picture. It is the two. So every complex curve is a real surface. So for this one, the picture is the sphere. So when the genus is equal to 1, C is called an elliptic curve. The picture is the second picture. So we see that, that there's a hole inside. So this hole corresponds to this 1. There's one hole, so the genus is 1. And we have other pictures. So these pictures, they correspond to curves with higher genus at least 2. So the number of holes are just the genus of the curves. So this is a very rough classification. But still, we have plenty reasons to make such a classification. For example, we can see that the first one, it is simply connected. The second one, it is not simply connected. Its fundamental group is infinite but abelian. So the fundamental group is Z2. And for all of these curves with higher genera, their fundamental groups are infinite and non-commutative. Also, from the viewpoint of differential geometry, we can see that this is positively curved. The curvature is positive. And this one, the curvature is 0, it's flat. And here, the curvatures are negative. So there are still some reasons that we do such a classification. So this is the case of curves. Now we pass to the classification of surfaces. So the classification of surfaces was already initiated by the Italian school in the late 19th century. So I list several names here. They are very frequently appear in the literature of algebraic geometry. However, starting from dimension 2, there is a new type of operation, which is called a blow up of a point. So in higher dimension, we can blow up subvarieties other than points. So we can visualize this operation in a picture. So imagine that this one is a complex surface, and we take 3 points in this complex surface. And we can blow up these points. For example, I blow up the first point. So the blow up just means that I can replace this point by a curve, and the remainder part remains the same. So these two surfaces, they are different. For example, we can see that the second Betti number, so the second cohomology group of this one is greater than this one. So this is the one blow up of the first point. And I can continue. I can blow up the second point. So I replace this point by a curve. And I can blow up the third point and so on. So these three surfaces, they are all obtained from the first surface. And also, if we ignore these points or these curves, the remainder parts are isomorphic. So this is the prototype of birational geometry. So we say that these four surfaces, they are birationally equivalent because outside some subvarieties of smaller dimension, they are the same. So they are roughly the same on large open subsets, and they are called birational. It is natural to classify X and its blow up in the same class because we know how to obtain one from the other. There is a powerful theorem due to Castelnuovo in 1900, which tells us if a surface is the blow up of the other surface. So I consider a surface Y. Assume that there is a rational curve inside this Y, such that it satisfies this C2, this so-called intersection, self-intersection is equal to -1. And this curve is called the -1 curve. Anyway, so if Y contains such a rational curve C, then we know that Y is the blow up of some other surface X. And in this blow up, C is the curve we obtain by the blowing up. So in other words, there is a morphism from Y to X such that the image of C in X is a point, and outside this curve, everything is isomorphic. Now with this theorem in hand, we start from some compact complex surface X. We can search if there are -1 curve inside. If there is one, I use this theorem to contract this curve. And then we obtain another surface, and I continue to find if there are some minus curve inside. For topological reason, for example, we can look at the second Petit number or the second cohomology group. You'll see that after finite many steps, we will arrive at a surface S, which contains no such a -1 curve. So, in other words, by this theorem, S is not the blow up of other surface. That's why we call such a surface S a minimal surface. So to be precise, a minimal surface is not the blow up of any other surface. And equivalently, a minimal surface is a surface which does not contain any -1 curve. So given any surface, we can find a minimal surface which is birational to it. And the remainder thing is to classify all minimal surfaces. And this is done by Enriquez in the 1910s for projective minimal surfaces. And for non-projective or non-algebraic minimal compact surfaces, they are classified by Kaehler, the same mathematician Kaehler as before in 1960s. So here is the list of the classification of minimal Kaehler surfaces. I underline that this is the classification of Kaehler surfaces. For all compact complex surfaces, there are two other types. And in this list, I use two colors. So I will first explain the three classification in blue. So the first one is P2. And I said this is the analog of P1. So this is easy to imagine because I just replace 1 by the dimension 2 here. So the first one is the analog P1. And the second one, I have a list. And this list, these surfaces can be also called Calabi-Yau surfaces. And this, I say, they are analog of elliptic curves. Indeed, these surfaces, they are richly flat due to Yau's theorem, and so that means their curvatures are flat. So which correspond to the case of elliptic curves, because we have seen that elliptic curves, their curvatures are flat. And the third type is a surface of general type. And I say that they are analog of high genus curves. And we can see that for these surfaces, their curvatures are negative. So these three items in blue, they are analog of the classification of curves. Now there are two new types in the case of surfaces. So the classification of surfaces is more complicated than the one of curves. So the first one is called a rule surface. And in this case, there is a morphism from this surface S to a curve B, such that the fibers of this morphism, they are curves. So this is two-dimensional maps to something of one-dimensional. Then the fibers, so which are contracted to points, they are one-dimensional. So in this case, all these fibers are P1. So I write that this is a mixture of P1 and some other curves B. And the fourth type, which is the second in black, we call it an elliptic surface. Again, there is a morphism from S to another curve B. But now the fibers, or smooth fibers, they are elliptic curves, not rational curves. And for this type, I call it the mixture of elliptic curves and some other curve. So briefly, a minimal compact Kaehler surface is either a mixture of curves, so those in black, or one of the analog of curves, one of these in blue. So this is the classification of minimal compact Kaehler surfaces. So after all, the theory works very well for surfaces. Now we want to proceed further to higher dimension. So we want to generalize the surface classification method to higher dimensions. If we review the classification of surfaces, we see that this will mainly consist of two steps. So the first step is to minimize a given compact complex variety or manifold. And now this is known as the minimal model program, so MMP for short. And if this is successful, if we find a minimal representative in this birational class of the given variety, then we want to classify the minimal varieties. And for this part, this is about this famous abundance conjecture. So what we know for now is that for threefolds, both 1 and 2, they are proved. So for projective varieties, they are proved by the end of 20th century. And for compact Kaehler varieties, they were proved in the past few years. And if the dimension is higher, so at least 4, for projective manifolds, the minimal model program exists. But we do not know if it terminates. So we have a strategy which directs to the minimal representative or the minimal variety. But we do not know if this strategy always stops. Of course, conjecturally, it will stop. So the termination problem is still unknown. And for the second part, for the abundance conjecture, little is known once the dimension is at least 4. So for this strategy, the first step is to find rational curves in a complex manifold. This is the higher dimensional generalization of this Castanoro theorem. So we want to detect if a variety is minimal. So we need to find rational curve at the very first step. So in higher dimension, we relax our definition. So a rational curve in a complex manifold or variety, it is just the image of P1. Of course, this image cannot be a point, but we do not require this image is smooth. So the P1 is smooth, the image may be singular. It turns out that this is quite a complicated and a difficult problem, as the dimension is at least 3. Mori, he made a breakthrough in 1979. Mori was just rewarded this ICPS prize very recently. So his famous theorem is also called the Bannon-Briggs theorem. The theorem says that if the canonical bundle or the canonical line bundle, so this is a line bundle which is defined in a canonical way on the variety or the manifold X. So for projective manifold, if this canonical line bundle is non-nav, then this manifold X contains a rational curve with this property. So non-nav, it just means that there is a curve in this X such that this product, this intersection product of this curve and this canonical bundle is negative. So Mori's Bannon-Briggs theorem proceeds very geometrically as follows. So imagine that, or we assume that this intersection number is extremely negative, not just negative, but extremely negative. So this is the curve D. And we fix 2 points inside X on this curve D. So once this intersection is extremely negative, we can deform this curve while making these 2 points fixed. And then we can continue to deform. So this is also called bending the curve. And if we deform sufficiently, then at the limit, this curve will break into at least 2 pieces. We can imagine this happening in the real world, right? When we bend a string, and if we bend sufficiently, it will break. And one of these curves will have a smaller genus. So we know that rational curve is the curve with the smallest genus 0. So we can continue to do this procedure to bending and breaking, and every time we reduce the genus, and finally we will obtain a rational curve. So this is the Mori's Bannon-Briggs theorem. So the key point is to obtain some intersection, some curve with extremely negative intersection. So this negativity should be very strong. But in general, we only have some negativity, but the negativity will not be strong. So to make this idea work, Mori's idea is to use this reduction modulo P. Here P stands for prime number. So roughly speaking, in the world of positive characteristic, we will have more deformations, and we will have deformation we will have deformation easier. Indeed, there is some so-called Frobenius map which can make this intersection number extremely negative. But the Frobenius map does not exist in the world of characteristic 0. So let me briefly explain the method modulo P, reduction modulo P. So we know that every projective manifold is defined by finitely many polynomial. So we take one polynomial. For simplicity, I assume this polynomial is with integer coefficient. Now take any prime number, say 3, and the reduction modulo P is just to reduce this polynomial modulo 3 here. Then we see that it becomes this polynomial. Its coefficient is in this finite field 0 over 3z. And we do this for every defining polynomial. And we will obtain some polynomials with coefficient in this finite field, and they will define some algebraic variety in the projective space over this finite field. And similarly, we can do this for another prime number 5, for example. So every time we do this reduction modulo some prime number P, we use this Frobenius map in positive characteristic to make the intersection number extremely negative. And then we can produce rational curve in the world of characteristic P. And this will work for most P. And it will imply that in characteristic 0, there is at least one rational curve. So this is the method of Mori. And of course, it only works for algebraic varieties because we need defining equations, and we need finite many equations and do the reduction. Now I introduce a notion. So compact complex manifold X is called uniruled if it is covered by rational curves. Miyaoka and Mori, they show that a projective manifold X is uniruled if and only if X is covered by curves D such that this intersection product is negative. Indeed, we just need to do this band break for each such a curve, and then we can produce a lot of rational curve, because by definition, through every point of X, there is such a curve D passing through that point and with this negative intersection. Later in 2004, Buxon, Demain, Pan, Peter Nell, they show that this condition, the later condition here, covered by curves with this property, is equivalent to that X is not pseudo-effective. So now we know that for projective manifolds, X is uniruled if and only if this canonical line bundle is not pseudo-effective. And these are true for projective manifolds. Now we pass to the problem of Kaehler manifolds. For compact Kaehler surfaces, this criterion also holds for compact Kaehler surfaces. And this is due to Yao in 1974. Of course, we observed that 1974 is earlier than Mori's theorem. Indeed, here Yao used the classification of surfaces and he produced require Kaehler matrix on the manifold. And for threefolds, Brunella proved the same characterization in 2006. Recently, we proved that this compact Kaehler manifold is uniruled if and only if K is not pseudo-effective. So we can generalize this criterion to all compact Kaehler manifolds. So I need to stress that, so we still need to use Mori's band-break theorem for projective manifolds. Indeed, our proof discusses non-projective compact Kaehler manifolds. And this condition will give some more information, and we can prove the uniruleness by non-algebraic methods. So a main ingredient in our proof is Demain's mass concentration. It is an application of Yao's famous theorem on the solution of Mongeon-Beck equations. Also, Guanzhou's optimal L2 extension plays a very important role in our proof. Now, combined with previous work, we know that if Kx is non-F for a compact Kaehler manifold, then X contains a rational curve. So Mori's first theorem also holds for compact Kaehler manifold. So this is due to Cao and Hori in 2020. Furthermore, for specialists, the Kong theorem also holds for compact Kaehler manifold. This is due to Haken and Pound in 2024. So I said that previously they assumed this theorem to prove their result. Now this theorem is proved, so every result here are valid. Now for minimal model programs, in order to catch up with projective manifolds, it remains to show the contraction theorem. Now assume everything works very well. So assume the minimal model program works and assume the abundance conjecture works, then we will have this conjectural classification. So starting with some compact Kaehler manifold, we use the minimal model program to find some minimal representative, which is a minimal Kaehler variety. Usually, it has singularities, so I use the word variety. And for this minimal, so-called minimal variety, we have 5 classifications, which is very similar to the classification of surfaces. There are 3 in blue. They are analog of curve classifications. So they are Fano varieties, Calabi-Yau varieties, and varieties of general type. And there are two other cases. And in this case, there is always a morphism. So the first one is Mori fiber space. So there is a morphism from X to some B, which is positive dimensional but with smaller dimension, such that the fibers, general fibers, are Fano varieties. So the fibers are smaller dimensional varieties of the first type, first blue type. So this is the first one, and this is the analog of ruled surface. And the second in black is there is a morphism from X to B, as here. B has positive dimensional, and the dimension of B is smaller than the dimension of X. And the general fibers are Calabi-Yau varieties. So general fibers are varieties of smaller dimension and of the second blue type. And this is the analog of elliptic surfaces. So maybe I also need to underline that this classification is not a disjoint union. For example, there are Fano varieties which also admits a structure of Mori fiber space. For example, we can take the product 2P2, then one projection will be a Mori fiber space, etc. So this is the very conjectural classification of higher dimensional compact Kaehler varieties. Okay, so let's come back to the previous problem. How far is a general Kaehler variety away from a projective variety? Indeed, this is also called the Cordella problem. So Cordella asks, is every compact Kaehler manifold approximable under deformation by projective manifolds? The answer is yes for surfaces. Cordella proved this for surfaces, and he asked for higher dimensional cases. And the answer is indeed negative, which might be surprising at that time. And this negative answer is given by Voisin. So when the dimension is at least 4, the Cordella problem does not hold. It has a negative answer. And quite recently, by Lin, he proved that the Cordella problem also has a positive answer if the dimension is 3. So the Cordella problem has negative answer in general in higher dimension. It says that in higher dimension, projective manifolds are relatively rare among Kaehler manifolds. However, if we look at the previous classification, the very conjectural classification for these minimal varieties, we see that there are 3 blue analog of curves, and they are Fano varieties, Calabi-Yau varieties, and varieties of general type. And so they are also often called the 3 building blocks for this birational classification. And for these 3 building block types, we first see that Fano type and general types, they are always projective. And for the Calabi-Yau types, the mildly singular Calabi-Yau types, they are approximable by projective varieties. So the 3 building blocks are still approximable by projective varieties. So this is due to Baker, Galanti, and Len in 2020. So maybe the effect from general Kaehler manifolds to projective manifolds, they are the fibrations in these 2 black classifications, or the blow-ups, or the birational transforms. Because the 3 building blocks, they are approximable by but they are approximable by projective varieties. So this might be a picture of the classification of the conjectural classification of compact Kaehler varieties. So in the last 5 minutes, I try to outline very briefly the proof of the theorem. So the theorem, I follow the methods of Brunella. So the difficult part is to produce rational curves. So I can assume that X is a compact Kaehler manifold such that the canonical omega X is not pseudo-effective. And we need to show that X is uniruled. As I mentioned, this is the difficult part. And again, we may assume that it is not projective. if it is projective, we can use the theorem of Mori and BDPP. Now, if it is not projective but Kaehler, by Cordela's embedding theorem, there is a non-zero holomorphic two-form sigma in this on this X. So sigma is a two-form globally on X. Now we can consider the contraction with sigma. So it goes from the tangent space to the cotangent space. Because it is a two-form, I contract it with some one vector, and where it remains, the output is a one form. So we have this morphism. This is a holomorphic morphism between holomorphic bundles. And we can define the kernel of this contraction, F. Then F is a coherent sheaf. And we can show that F is indeed non-zero, and F is different from Tx. Indeed, if F is equal to Tx, then this sigma must be 0. So this is not the case. If F is equal to 0, we will see that omega x will have global sections, which contradict the fact that it is not pseudo-effective. So F is non-zero, and the rank is between 0 and the dimension of x. Now I use the condition that x is Kaehler, and we have Hodge theory for Kaehler manifolds, compact Kaehler manifolds. And this will show that sigma is, this holomorphic form is indeed a closed differential form. And hence, by this Cardon calculus, we deduce that F is indeed a foliation on X, which means that on the locus where F is a subbundle, it is closed under the Lie bracket. So in the situation of Brunella for threefolds, we will very easily deduce that F star is non-pseudo-effective line bundle, which means F star is negative. So pseudo-effective means some positivity. So it's non-pseudo-effective, so I write it in this way. F star is negative. And he managed to show that for this foliation, the closure of the leaves are rational curves. In particular, F is induced by a homomorphic map. So that the F is indeed the relative tangent of this map. And the two form comes from Y. And the fibers here, they are rational curves. So X is covered by rational curves and uniruled. So this is what Brunella proved in 2006. So in higher dimension, we want to prove something similar. But it's more involved because in this case, this is a foliation of rank 1. At that time, Brunella's method does not extend to higher dimension. In higher dimension, we first consider some so-called maximal destabilizer f prime of f. And we will obtain this f prime, which is a foliation, and it is non-pseudo-effective as a coherent sheaf of higher rank. We can still write f prime star negative. And the most important step to prove is to show that this f prime is induced by a homomorphic map. And once we can show that it's induced by this homomorphic map, we can also show that the two-form sigma comes from Y. So now we produce an additional structure, which from X to Y, and the dimension Y is between X and 0. And the remainder is just to prove by induction on dimensions. And that's the idea of our proof. Okay, I think I will stop here. Thank you for your attention.